I'll be talking about the terrestrial lidar and its application. Terrestrial lidar is a remote sensing technique which acquires the geometrical data of the scene, and the lidar sensor basically employs its own source of light for acquiring the geometrical property of the target. In case of lidar, the light in very special form called laser will be used. Stands for light amplification by stimulated emission of radiation. Laser has got certain properties like it is highly directional, it is highly energetic, it is monochromatic, which means that it has got a single wavelength and single color, and also it is coherent. These properties of the laser makes the lidar data very special, and in lidar basically these lasers will be fired onto the ground, and wherever the laser touches we get the coordinate of that particular points. So this way the lidar technology basically becomes a non-imaging technique, unlike the other remote sensings like acquiring the images. And the end product that we expect from the lidar is the geometrical property of the scene, and the feature identification can only be done based upon the geometry. Since it is monochromatic, we will not be able to identify the object based upon the spectral properties. So ultimately the thing that we get from the lidar is the geometry of the scene, either the surfaces or the measurements or the 3D profile of the scene. In case of lidar, the data acquisition is done by firing the laser pulses onto the ground. When this laser pulses touches the ground, a particular area will be illuminated by the laser. That area is called as the footprint, and the lidar data basically consists of the location of the footprint in terms of x, y, z, or the latitude, longitude, elevation of the footprint, along with the intensity, which represents the backscattered light ray. So this way, this is basically a non-imaging technique, unlike the normal photographs where the entire scene will be captured. When we compare the lidar technique with the other remote sensing, since it is non-imaging, the data that we get is not continuous over the scene or over the terrain. However, it is not continuous. Even then we will get very precise details of the ground. Like in this photograph, we can see that even the transmission wires are being mapped. Such data acquisition with other remote sensing techniques is not possible. Since the lasers are very highly directional, the laser which are hitting the transmission wires are mapped, and this lidar technology has greater potential in mapping the transmission wires. And also we can see here that we can get the vertical profile of the ground. In the images we get only the planimetry, but in the lidar technique we get the vertical profile of the ground also. Since the lasers are very highly energetic, they can penetrate into the water and also the canopy. Like we can see here that a laser is being fired from the aircraft which touches the surface of the water, and further because of its high energetic nature it can penetrate into the water, and then we can get some reflectance from the bottom of the water body also. So this way we can map the surface of the water and also the bed of the water. So at the sensor we get the signal something like this. So this signal corresponds to the surface of the water, and this signal corresponds to the bed of the water body. So this way the bathymetry can be performed using the laser. However, care has to be taken that the wavelength of the laser should not be in the infrared region if we are going for the bathymetry. We normally go for red lasers or blue lasers, or a combination of red and blue for mapping the water body floor. And coming to the penetration by the canopy, since the lasers are highly energetic, the laser light that is coming from the lidar sensor hits the top of the canopy, and if there are gaps, the laser can go into the canopy and touch the intermediate surfaces like branches, leaves and other surfaces, and we can expect some returns from the inside the canopy also. And if there are some more gaps left, then the laser can go and penetrate the ground below, and then we can expect some more return from the ground also. This way the entire laser energy that is reflected back can be mapped as the waveform like this. So in this we can see that the return which we get earlier, we call it as the first return, and the return that we get lastly is called as the last return, and we have some more intermediate returns. So this way we call it as the first return, second return, third return, fourth return and the last return. Normally the last returns are from the ground and first returns are from the top of the canopy. If you obtain a lidar data for a particular tree, then the lidar data obtained for the tree can be seen here, and the coloring is given based upon the returns. Red color is with the first return, blue color is for the second return, and green and the yellow color is for the third return, that is the last return. So this way the LiDAR data of this particular tree can be used for getting the forest inventory, estimating the biomass, and we can also estimate what is the height of the tree, what is the crown diameter, what is the diameter of the stem. All these parameters of the tree can be automatically extracted. And further we can also estimate the leaf area index, and nowadays there are algorithms which can find out how many leaves are there in the tree. So that way this technology has very prominent role in estimating the forest inventory. And the data acquisition for the LiDAR can be done at 3 different platforms as done for any remote sensing, that is ground based, aerial and space based. In space based, basically the laser scanner instrument or payload will be mounted on an mounted on a satellite, and the examples of such missions are ISAT, Chandrayaan-1, Light, SLA and Calypso. These are the satellites which have carried the laser payloads. ISAT was basically for ice, cloud and land elevation satellite, basically for measuring the topography of the ground and estimating the changes in the ice sheet. And in the LLR and in Chandrayaan there was a payload LLRI, which stands for Lunar Laser Ranging Instrument, which was basically for mapping the topography of the lunar surface. And in case of aerial, we can have 2 modes. One is a manned aircraft, and another thing is the unmanned aerial vehicles. And we can mount the laser scanner on an aircraft which is operated by a pilot who is on board the aircraft. This is one of the conventional aerial platform, but nowadays because of the miniaturization of the electronics and the instrumentation, the laser scanners can be mounted on UAVs or drones, which can be easily maneuvered and which can be easily deployed for the shorter areas. So these UAVs are nowadays becoming new emerging platforms for remote sensing, because they are very economical, especially for very smaller regions. Going for manned missions for a smaller regions will be a very costly affair, unlike the unmanned aerial vehicles. And coming to the ground platform, which will also be called as the terrestrial platforms. So in case of terrestrial platform, the the LiDAR data can be acquired either in static mode or in the mobile mode. In case of static mode, the laser scanner, which looks something like this, will be mounted on a tripod, and then the various operations are done so that we are acquiring the laser data of a desired scene. Whereas in case of mobile, the laser scanner will be mounted on a car, and the car will be moving, and simultaneously the data will be acquired, so that we are mapping the assets of the road and we are mapping the condition of the road. So this way there are some new platforms are coming up for the LiDAR and also for any remote sensing. One is a mobile one, another is the making use of drones for acquiring the data. In case of terrestrial laser scanning, the data acquisition is done in horizontal and vertical fashion. This laser scanner will have a laser emitter, which basically emits a laser pulse, so that we are exposing a certain portion on the scene, and then the laser will be fired at a certain different angle, and similarly the laser data will be acquired in a line fashion, which is shown here like this, so from top to bottom. And once the data is acquired in this line fashion, then the terrestrial laser scanner rotates slightly in the horizontal direction, so that the second line is obtained, and further the increment will be done for the horizontal angle, so that the third line is scanned. Since it is discrete, so we get the discrete points on the scene, and this the increment of vertical angle and horizontal angle can be provided by the user, and this will be decided based upon how much data density we want on a scene. And the accuracy that we obtain with the TLS is of the order of few millimeters or few centimeters. And coming to the types of the laser scanner, we can have 3 types of laser scanner. One is a camera scanner, panoramic scanner and a hybrid scanner. Camera scanner is very much similar to our normal camera, where we have a limited field of view, like we can have a field of view of 40 degrees by 40 degrees in vertical and horizontal, and which is very much similar to our normal consumer grade cameras. These kind of laser scanners can be used for basically getting the data that is to be obtained from the outside of an object. And for such scanners, we normally go for a longer ranging devices. Now coming to the panoramic scanners, where the field of view is very large when compared to the camera based, and the field of view is only limited by the base of the scanner. And these types are normally used for mapping the indoor purpose or for also the outdoor purpose, like digitizing the room and various facilities present inside a room or inside an industry, and also this can be used for outdoor mapping. And there are also hybrid scanner, which are a kind of combination of both camera scanner and panoramic scanner. So in this one we have one rotation axis without any restriction, in which the laser scanner will be rotating in the horizontal direction, whereas the vertical rotation will be controlled by a rotating mirror. And here we can have our own desired field of view, that in case of the vertical we can have a vertical view of 100 degrees, and the horizontal can be entire 360 degrees. And also the user can give a selected area of interest in which he wants to do the scanning. So here are some pictures showing you in panoramic scanner we can scan the entire area, entire 360 degree by 360 degree. In case of hybrid, we can choose which kind of area we want to acquire, and in case of the camera scanner, only a limited portion of the entire space can be acquired to get the 3D data of the scene. And this terrestrial laser scanner can also be divided based upon their nature. One is the dynamic, which comes into the category of mobile mapping, in which the laser scanner will be mounted on a moving platform like car or a boat, and then the data is acquired, especially for mapping the roads or the tracks, or basically for the mobile mapping purpose. And in the case of static, the laser scanners can be divided based upon the range. The range basically tells that how far a laser scanner can record the data. Like in long ranges, basically the distance is 150 meters to 1 kilometers. In medium range, it is from 1 meter to 150 meter. In case of close range, the distance that can be mapped is from 0.5 meter to at most 2 meters. So any object which is beyond 2 meters will not be mapped or scanned. So the long range basically are done for the monitoring purpose, or for city modeling, or for some applications like in case of mining. Whereas the medium range are normally for mapping the facility management, for mapping the industrial infrastructure, for various infrastructures in the civil engineering domain, for geological studies, for the study of architecture and cultural heritage monitoring. These kinds of medium range laser scanners can be employed. And this close range are normally for very precise measurements and very dense measurements, like we use in case of reverse engineering. Once there is any model, we have to prepare a digital model of the analytical model. Then in such cases we go for very close range kind of laser scanner for scanning the body, for measuring any deformation, in case of the medical mapping of any object, and also in case of police investigations. If some incident or accident had happened, then the police department can make use of this close range in order to map it and further analyze and further investigate into the case. And now coming to the applications of this terrestrial laser scanner, there are wide number of applications. So I'll go through the possible applications and also some case studies which we have taken up at our institute. Especially this TLS has got a lot of application in 3D modeling for the indoor environments, like mapping the industrial infrastructure, mapping the pipelines and various infrastructure related to the industry. And also this can be used for mapping the objects which are of geological interest, and for 3D modeling of the various objects. And the objects can be of interest from archaeological point of view, or also from the application point of view, like in case of generating the 3D models or acquiring the data of the power stations. Here we can see that even the transmission lines are very nicely mapped. So if there is any sagging, or if some repair work or some maintenance work has to be done, so this can be basically assessed from this 3D data acquired from TLS, and then accordingly suitable measures can be taken for maintaining the power related infrastructures. And also for the monuments, the 3D models can be reconstructed at various scales, and this can be further used for monitoring or conserving them. And apart from this TLS can be used for the monitoring monitoring various activities, like just like monitoring the mining activity. So in the mining areas, the TLS data can be acquired at regular interval basis, which can be decided by the supervisor who is handling at the mining site. And for mining site, we can generate the surfaces at regular intervals, and then comparing these two surfaces which are acquired at different intervals, we can estimate how much amount of volume is excavated, and then accordingly the monitoring of this can be done. Apart from the mining, we can also do the monitoring of the structures. The structure is the very important structures like the dams and bridges can be monitored to assess their health, and if the health is deteriorating, then then suitable measures can be done so that we are maintaining the required strength of that monument. So here we can do the scanning of the dam from various points, and then we can make a model of the dam, and then when different loads are applied on the model, like we have the water level is so much, and here if the water level is increasing, then what should be the allowable deformation in the dam, and if the deformation is more than the allowable, then suitable measures have to be taken so that we are doing the conservation of the dam. Otherwise it is possible that because of this heavy load and also poor health of this dam, then the dam may be may get destroyed, and then the water may be flowing out. So such kinds of monitoring and conservation methods can be carried out for making the structural health and maintaining the health of the monuments. And also this TLS can be used for monitoring the various construction activities of large infrastructure, or basically for monitoring the conditions of the road. So apart from that, TLS has also a greater role in digitally documenting these cultural heritage sites. As these cultural heritage sites are very, very precious in the interest of nation, and also there are some worldwide protected heritage sites which needs to be digitally documented, and these digitally documented sites can be used in case where we have a disaster, or where some deformation happen in the structure, and then we can take up the reconstruction activity. So for that purpose, we can acquire the TLS data from various different locations, and this data can be clubbed together so that we have a 3D model reconstructed. Since the LiDAR data can give very, very precise measurement, like we can see here, the finer details of the railing are acquired, and also the minor carvings are also being mapped very nicely with the TLS data. And this TLS data or terrestrial lasers can also be used basically for getting the forest inventory, estimating the biomass, and then further they can be linked with the carbon stocks in the forest. And for acquiring that, one can acquire the TLS data with various resolutions. This will depend upon the what is the size of plot, and what is the maximum height of the plant in a particular plot. So we designed a particular fashion that the TLS has to be kept at this four different corners, and also the acquisition should be done from the center, so that the entire trees are being collected in the point cloud of the TLS. So various settings can be applied at 1, 2, 3, 4, and at 5 the horizontal angle can be kept as the entire 360 degrees. And once we acquire the data from such 5 different locations, these entire data can be merged together, and we can have the visualization of the particular plot like this. And from this plot, we can try to estimate various forest inventory parameters like the height of the tree, the crown diameter, the diameter of the stems, and we can finally try to get the volume of the stems. So here each tree is separated out, and from this tree, by applying this octree filtration, we can remove the branches from the other trees and also the leaves of this tree, so that we are only getting the point cloud corresponding to the particular tree. And from this, we can estimate what is the volume of this particular stem by slicing this point cloud at different level, and by using this cylinder or cone formula, we can estimate what is the volume. And similarly, we can repeat this for all the plants which are there, all the trees which are there in a plot, and then we can estimate the entire biomass, and all this approach can be automated to extract the forest inventory from the laser data. Apart from this, the TLS can also be used for studying the disaster loss because of various disaster events like landslide and flooding. So here is one case study which we have taken up at IRS. So this particular site is prone to both landslide. Here is a sliding area which is prone to slide when there is a slight amount of rainfall, and there are some houses constructed where on the riverbed itself. So when there is heavy rainfall, then there is a chance of having the flood in this case. So for this particular area, the surface was generated using the terrestrial laser scanner, and on this surface we have done the modeling so that we estimate when there is a rainfall, then because of this rainfall, how much amount of debris are going to fall because of the landslide. So here we can estimate that if a landslide is triggered, then which are those houses which will be affected, and how much will be the amount of loss, basically in terms of the property and also in terms of population, if we geotag each of the 3D model of the houses with the amount of population and also attribute the value of that. So we can estimate here and see that which are those houses affected, and ultimately we can make an assessment of the disaster loss. And then we can take preventive measures, whether we allow a colony to be developed here, or what kind of different measures we can take up. And also we can make the simulations of flood once we have the TLS surface generated from the TLS data, and also the 3D models which are created from the closed-end photographs. Then we can develop the scenario that if certain amount of rainfall happens, then how the water is going to flow and which are those buildings which will be affected. So this way we can estimate the amount of loss, basically because of the disasters like the flooding and also the landslide. So these two case studies were done at the same sites which were prone to both landslide as well as the flooding. And also we very pictorially we can show that this is the river stream, and using the TLS data and surface and various hydrological model, we can see that if there is a slight rise in the water level, then which are those buildings which will be affected. So here we can see, and also parallelly we can estimate how much will be the property loss. So apart from this, we can also make use of TLS for mapping the landslide area. So one case study was done on a landslide which is near to the Kalia shore, or sometimes it is called as Shiroba Bag landslide, which is on the National Highway 51 on the way to Badrinath. And there are a lot of activities happening here, because of which this highway gets blocked up many times. So in order to make some controlling measure for that, the TLS data was acquired from different locations, and the TLS data was merged to have the digital surface generated, and from this digital surface we can estimate the slope map, and this slope maps plays one of the major role along with the other geological parameters to estimate the landslide activities that are going to happen. And from the surface that is generated from the TLS data, we can estimate the various profiles, and these profiles will be very much useful for the landslide analysis using other geological data along with it. And now coming to the demonstration of the TLS. TLS is normally mounted on a tripod if we are acquiring the data on in a static mode. So this TLS basically has got two parts. One is stationary part, another is the rotating part. The stationary part is normally attached with the tripod, and the rotating part is above head, and this rotating part will rotate 360 degrees, and inside TLS there is a mirror which tilts so that we have the vertical field of view, and horizontal field of view will be provided by rotating the TLS. And this TLS are normally equipped with camera, so you can mount a camera, and on the camera you can also place the GPS so that we can georeference the data that we obtain from the TLS. And this TLS data can be connected with laptop so that we can do the operations on the TLS. The various operations that we do on the TLS is, firstly we define how much area we want to collect, and within this area we have to give how much increment we want to have for the horizontal and also for the vertical. Accordingly the data will be collected. So in order to operate that, for each instrument there will be a software provided. So the demonstration is being done with the Regal TLS. With this instrument we have a software called Rescan Pro. In this software, initially we have to create a new project. As soon as we create a new project, it will facilitate us to store the data where we can browse to the location where the entire data can be stored. And once we give the name of the project and also the location, then these files will be generated, which will have the calibration file. Basically this calibration file is the calibration between the camera and the TLS, and also a folder for various views after the data is collected, and other things which will help in merging the data and also different kinds of visualization. So initially, as soon as the project is created, simply we have to right click on the scan folder, and then these are the various options available. So simply we have to click on this new scan position. So as soon as you click on new scan position, we will be given with this pop-up window where we can name the scan. Like if we are going to scan a particular object, then we may be doing it from different locations. So for this particular station 1, we can give the naming like station 1 or scan 1. So this way we can give the naming here. So as soon as you click here OK, the window goes off, and then we have to select the instrument here. That can be done by clicking on the a module called scanner search network. So as soon as you search in that, the scanner that is attached with your laptop get connected, and then as soon as it collect, we'll have a facility of the scan position name which is given here. So simply we have to right click on this, and we have to say that we are acquiring a new single scan. Okay, so then accordingly the naming has to be done, and then we have to give the various description that how much amount of increment we are going to make in terms of horizontal and also in the vertical. And once those things are done, then the operation of the TLS starts, and the data is acquired both in horizontal and vertical. You can see that this is the position of the laser scanner, and the entire scene of 360 degree is acquired, and also in terms of vertical, since in the case of vertical the angle was given up to 100 degrees, so only certain area just above the TLS was not acquired, and this TLS data can be visualized. Okay, so once the data is collected from various locations, like one scan position was from here, another scan position was here, and another scan position was from here, and also some data was taken indoor. After merging the TLS data, we can obtain the 3D model of this particular building from outside and also from inside. The data for this particular site was captured from various locations, and ultimately the data is merged so that a 3D model of this monument can be created. So here is a case study which was taken up especially for this landslide on the National Highway 58 on the way to Badrinath. This landslide was mapped from various locations, and then the data was integrated. So this merged TLS data has given the entire profile of the landslide, which will go as one of the very important inputs basically for monitoring and taking up the conservation activities related to this landslide. So we can see here some conservation activities are already there by constructing a barrier to prevent the debris that are falling from up. So I hope this lecture has provided you a brief overview of the TLS and its possible applications. Thank you.